Alright, ladies and gentlemen, let's learn a little bit more about the chemistry behind nuclear waste and its disposal. So at this point you will have learned about the nuclear waste that's generated by nuclear power plants, where it is, where it isn't, etc. But none of this means a lot without a strong grounding in chemistry, or at least it won't mean as much to you as it could without a strong grounding in chemistry. So I want you to take a look at this diagram, nuclear waste and its disposal, and what you'll notice is that we've got uranium-238 up here in the corner. And remember, uranium-238 is not the fissile isotope, meaning this is the stuff that might be like 95% of the fuel we use for nuclear power, and once uranium-235 has all been used up to generate power, this is what's left over. Here's the problem. Nuclear waste doesn't just sit there happily, it's actually in the process of decaying. And that's what you see going on here. We're literally charting the decay process that will happen. So uranium-238 will decay into thorium-234. And how fast will that happen? Well, over the course of about 4.5 billion years. That's the half-life. That's sort of like the average time it takes. And how does it do that? Well, this nucleus is going to, instead of splitting like in fission, it's just going to throw off a particle. And that's what you see right there. That little A means alpha particle. Okay, an alpha particle. You'll learn more about those in our radiation lab. So it gets rid of that alpha particle, and you'll notice uranium-238 has 92 protons. Thorium-234 has 90 protons. So it's lost 2 protons. What else has it lost? If you do your math, 238 minus 234, it lost 4 particles total. 2 of them were protons, so the other 2 must be neutrons. So that's what an alpha particle is. 2 protons and 2 neutrons went flying off. We get thorium-234. That takes about 27 days on average to decay. When it does, it gets rid of a beta particle. All right, and that just keeps going on, and each of these takes a different amount of time. But this process goes on and on and on and on and on until eventually we reach some stable isotope. Now it's different for, friend, I need you to focus. It's different for every sort of pathway, but down here you'll see at the very bottom, lead-206 finally says stable instead of having a half-life. And in that case, it means it does not decay. Which is another way, for our purposes, of saying is not radioactive. Does not decay, so it's not radioactive. So let's talk a little bit about this radioactive decay so that we can be a little bit clearer about what's happening. Let's go back up here to the top of the page. So nuclear waste is things, elements that are actively undergoing radioactive decay. So let's add a little bit of this here. Waste. It's any leftover from a nuclear process actively undergoing radioactive decay. And you might notice that my paper has these little names right here and yours doesn't. That's okay. This is my first draft of this set of notes and I'm using old sheets, but you'll have nicer ones for you by the time you see this. So when we say radioactive decay, what we mean is that an unstable nucleus is sort of spontaneously disintegrating. Spontaneously is hard for me to spell. And in this case, when we say disintegrates, what we mean is breaks down. Not splits, but literally just sort of breaks apart. It loses just a couple of particles. Right. If you hear any background noise, it's because I'm doing this at my house today, and the UPS truck just pulled up. All of the details you wanted about my life. All right, so when it breaks down, or disintegrates, when that happens, it releases those particles and also some energy, and that is what we call radiation. So let's do an example of radiation to make this make a little bit more sense. Here's one of my favorite examples. You know you're a chemistry teacher when you have favorite examples of radiation. Let's do thorium-230. That's this little guy right here. Let's imagine that it's been 4.5 billion years, 27 days, 1.17 minutes, 245,000 years, and then about another 75,000 years. Okay, and it's finally time for this piece of the remaining nuclear waste to decay. So we're going to write 230 thorium, and you might ask, how do we know these? Great question. I'll teach you about it in the lab. And as it breaks down, it's going to release an alpha particle. Okay, and as we already figured out, that's 4 protons and neutrons, and 2 of those specifically are protons, meaning the others are neutrons. So that's our alpha particle. It's also going to release a lot of gamma radiation. That's our symbol for gamma. That means it's essentially just energy. We'll talk about it soon. And what's going to be left over? Well, 230 minus 4 is going to be 226. And if 2 of those were protons, it's going to go down 2 in its atomic number, which means it's going to be radium. So here we go. Radium-226. So when we say radiation, what we mean is that something breaks down and releases particles, energy, or both. Okay? And what you're left with is a new nucleus. And that itself might be unstable and about to begin decaying. So that is what we mean when we say radioactive decay. Now, this is where things get a little spicy. All radioactive isotopes eventually decay. Every single one of them. So it doesn't really matter what you're left with. If the nucleus isn't stable, that means it is going to decay. So we're just going to do your favorite shape. I know how much you love to draw those. Okay. You could just skip it if you wanted to. So all radioactive isotopes eventually decay, and when they do, they release something called ionizing radiation. And we're going to come back to that. But for now, let's just add it, and then we'll focus in on the word decay. So when we say decay, we mean this breaking apart process, and the speed at which it happens, or I guess the rate at which it happens, is we measure that in terms of half-life. So that's sort of the eventually part of this. Half-life is the time required for half of however much of the starting material we had to decay, releasing that radiation. So let's add that. Okay, our abbreviation for half-life is T, lowercase, with a subscript, 1/2. So if you ever see T 1/2 written like that, it means half of the time, or in this case, half-life. And there's a hyphen there in the middle, I forgot. So half-life is the time required for 50% of the starting material to decay. So let's do a little bit of practice on this. Before we look at any complicated graphs, I just want you, excuse me, to take a look at these guys down here and take a look at the half-life for me. What's the half-life of radium? Oops, excuse me. What's the half-life of radium? Okay, well, it's 1,602 years. So another way to write that would be 1.6 lowercase k for kilo, that means 1,000, a for annums, which means years, okay? Another way to write that, so this would be T 1/2, 1.6 thousand years. Another way to write it would be 1.6 times, and I'm rounding a little bit here because I didn't keep the O2, times 10 to the 123 years. We've got a couple different ways we could write that. And when it does, it throws off an alpha particle and creates Rn, which I believe is radon, but it's slipping my mind right now. How long does it take radon to decay? Well, 3.8 days. So in this case, the half-life was equal to 3.8 days, and I don't have a fancy abbreviation for you there. Which one of these is more stable? Well, if it takes longer to decay, it's more stable. So this is an example of a more stable isotope. This is an example of a less stable isotope. A spicy question is, which would you prefer? This one's way more radioactive, but you don't have to plan very long for it. This one, on the other hand, is not as radioactive. It's not throwing off as much energy, per year, per hour, per day, but you have to plan on it for a really long time. So this is the point where I actually want you to start thinking about what it means when we say a really long time. I'm going to connect a video here if I can figure out how to do it, but keep in mind, 1.6 thousand years ago, English was not spoken anywhere on the planet. In fact, the language that was closest to English that was spoken was a Germanic language that you would not recognize. What would it mean to communicate with them? Well, it would mean learning another language. But we actually know that language was spoken. We've got records of that. Let's think about the other direction. If we've got a bunch of radium sitting around, what would it look like to communicate with people 1.6 thousand years in the future that this stuff is dangerous? Just think about that for a second. It's not like looking backward. We know what the language was. We don't know what the language will be in the future. It might even be hard to use symbols. It's such a tricky task. And this is radium. This is not even that stable an isotope. Look at thorium. How would you communicate with somebody 70,000 years in the future? Honestly, I don't even know that it can be possible with any kind of fidelity. So, truthfully, we're starting to think like, gosh, I hope the Lord comes back, because this is just so brutal to even consider. What are we going to do with these radioactive materials? As like a side note, I've got some units for you that will be in another reading that can help you sort of measure this radiation. But on the inside of this is a little bit more information about nuclear power, what is nuclear waste, what types of nuclear waste do we generate, what are some ideas about storage and disposal, and then I'm also going to link a video that's worth watching. Now, do you have to go through this all with a fine-tooth comb? No, you do not. But if I were about to sit on an expert panel and answer who knows what question, I might want extra depth of knowledge. So that's my suggestion to you, if you'll take it. So this is sort of a simple diagram of one particular half-life pathway via radioactive decay, etc., etc. But let's take a look at how we can estimate the half-life. You won't normally be given this kind of a diagram. You're more likely to see this as a graph. So let's continue on here. So once again, when we say half-life, we're talking about the time it takes for 1/2 of the material to decay. And when we say radioisotopes, we're talking about any unstable nuclei. It's literally radio, meaning electromagnetic radiation is being emitted, and isotopes, meaning isotopes. So isotopes that emit electromagnetic radiation. So this is any kind of unstable nuclei. And that happens as they decay. So before we go too far into this, I want to remind you, this would be a great time to review electromagnetic radiation. We haven't done a ton with it since Unit 1. So I want you to pause here, flip back in your notebook, and see if you can find electromagnetic radiation. It's way back there, but it is very important. In my notebook, I've got it on page 17. So go and take a quick look at that, and I'm going to add in right here, so you can go take a look. Page 17, and I'm also going to add it to our notebook over here, because when I said ionizing radiation earlier, that radiation we're talking about is once again electromagnetic radiation, so I'm going to add page 17 there as well. Okay. You'll notice on the far side of that electromagnetic spectrum, you're going to see X-rays and gamma rays, and that's what we're talking about when we say radiation. So let's estimate some half-lives. Okay, here's a very common graph. We've got cobalt-60, and it appears we start with 10 grams. So we'll do a cobalt-60 problem. Start with 10 grams. How much cobalt-60 will you have when half of it has decayed? Well, don't overthink this. Your amount left at time 1/2, meaning at 50%, would be 50%. What's 50% of 10? 5 grams. So take a look. Do you see 5 grams on here? Yep, right there. So we can do grams, how much remaining, and go all the way over from 50% to the 5 gram mark. And then we can go downward on this graph, and you'll notice it doesn't actually give us time here, it gives us number of half-lives. So after one half-life, okay, we have 50% left. But remember, the rest of it still has to decay, and do you see that this curve is sort of the opposite of exponential? Okay? So how long will it take for another half of that to decay? Well, another half-life. Then we'll have 2.5 grams, then we'll have 1.25, and every time you give it a half-life, in this case 5.27 years, every time you do that, you get half remaining. So how many half-lives will it take for this to be completely gone? Well, you would have to keep going down in the weight until you got to less than the weight of cobalt-60, which is about 60 AMUs. That's a really long time, folks. We're talking about 5.27 years, but how many times do you have to wait that for us to get down to almost none? That's why half-life is such a big deal. So let's add a little note there. Okay, this is loses half of its mass each half-life. But if we just keep dividing by 2 over and over, it still takes a really long time for us to end up with no cobalt-60. In fact, it will never actually approach 0, but eventually it will approach the weight of 1 atom, and at that point we can say it's all gone. So let's take a look at another example problem here. What are we looking at here? Phosphorus 32 and sulfur 32. Ooh, that's tricky. Phosphorus 32 and sulfur 32. So how do you know which one of those we start with and which one we end with? Well, you can look here at the beginning. At time 0, we have 100% of phosphorus 32. And by 145 days, oh, excuse me, that's 14.5 days, we have 50% of each. So it must be phosphorus decaying into sulfur. And the point at which we have 50% is 14.5 days, so that must be our half-life. So you don't really know, these graphs come in so many different types. Your job is to figure out in each graph what is the half-life. So let's take a look at another couple of examples. I actually want you to pause the video and see if you can do these two on your own. Did you pause it? Okay, here we go. So on this one, on the y-axis, we have the radioisotope percentage. That's how much is left. Half-life is when we have 50% left. So I'm going to draw sort of a dashed line at the 50% mark all the way across. And there are so many ways to figure this out, but this is my favorite way. And we're going to see when does each of these curves touch the line. Now, these curves represent yttrium-90, iodine-131, and copper-64 as they decay. And this is how much of that isotope you've got left, and this is how much time you've got. So the first curve I hit is yttrium-90, so that's the point at which I hit it, and I'm going to put a little dashed line going downward. Yttrium-90 finishes decaying right about here. What would you call that? It's maybe a third of the way to 50, maybe a little less. I'm going to estimate that for yttrium-90, we've got a half-life of, gosh, what's a third of 50? I'm going 15. Is that true? It's a good estimate. And that's hours. So after 15 hours, you've lost half of your yttrium-90. Alright, let's take a look at iodine-131. So we're going over. This is where it hits the 50% line. We're drawing our little line down. Where would you say that is? Maybe like, let's see, 20, 40, 60? Maybe that's 60 right there. So I would say that iodine-131 has a half-life of about 60, one of my units, hours. So these must be really unstable isotopes if it's only taken them 15 or 60 hours to decay. Okay, if you've been getting these wrong, you've been struggling with these, take a second, figure out copper-64 again. So 50% line goes all the way over. This is where it hits, this is where my decay curve hits the 50% line. Drawing this down. Looks like about 200 hours for copper-64. So that would be the half-life for that one. So let's take a look at this next one. This is the decay of carbon-14, and that ends up being a very important chemical in our world, or in our understanding of the history of Earth, at least from a science perspective. So let's take a look here. This is percent of carbon-14 atoms remaining. Where's your 50% line there? Well, it actually doesn't have it on this y-axis, but we know it's between 60 and 40, so it's right here. So I'm going to draw my line across. It hits the curve right here. I'm going to draw my dashed line going down. How long does it take? Well, I would say the half-life for carbon-14, based on this graph, what would you go, 6,000, 6,500? About 6,500 years. And again, this is just an estimation, which actually brings me to another piece of learning that you should opt into. On the inside of this, you can learn about how carbon dating works. Okay. Ooh, look, our half-life, 5,700. We were off, but not crazy off. Okay. So this is how carbon dating works. The important thing to know here is that when a nitrogen hits nitrogen-14, it makes carbon-14. A neutron, hits nitrogen-14. This really only happens in the atmosphere. So then if that carbon-14 gets pulled into the biosphere and gets buried, we can actually use the half-life to figure out how long that carbon's been buried, which can help us sort of date things. So I'd like you to read through this. This is an important thing to understand. When scientists come up with these like ages of things and they say we think it's this old or this old, this is how they're figuring that out. Now, are there caveats to this? Absolutely. But if you're looking for an understanding via science, we need to be supporting by evidence. This is the best evidence we've got for some of these ages of things. Now, if you don't love this and you want to move away from understanding the age of things via evidence, that's totally fine, but that does mean you're leaving the realm of science and you've moved into philosophy, literature, history, things like that. So if you're trying to figure it out with evidence, carbon-14 is one of our best methods. Not our only, though. So let's take a look at some other isotopes down here at the bottom. We've got some unusual versions. Right here, if you can read this incredibly tiny diagram, you'll see it's telling you these breakdowns are happening via alpha decay, but it's also giving you a little tiny half-life there, and that A means years. That's anoms. Okay. So over here, my paper says billion years. Yours will actually probably use GA. GA is giga-anoms. Giga, remember, means a billion. So a billion years, giga-anoms. So you tell me, thorium-234, when do you think we'll hit 50%? Uranium-238, when do you think we'll hit 50%? Go ahead and pause, do some thinking, give me an estimation. What do you think the half-life is? Did you pause? Alright, here we go. 50% is going to fall just a little below this 56 mark. Now we could draw out a graph and do this visually, but I'm also okay with just an estimation. Between 20 and 30 days, a little farther than 20, I'm going to say that the half-life of thorium-234 is about, let's go 21 days. And truthfully, I would give you credit for it if you picked anything between 20 and 30 that was closer to 20. Okay, these are really estimations that we're doing. So if that threw you for a loop, pause, try uranium-238 again. Alright. Where's the 50% mark? Well, it's going to be right about here. Once again, it's right below 54%. 4 billion years, 9 billion years. What's a little bit past 4 billion years? I would say the half-life based on this data is about, let's go 4.5 billion years. You could go 5 billion, that would be fine too. I'm not gonna split hairs on this. As long as you're between 4 and 9 billion and you're closer to 4, because 50% is closer to 54% than it is to 25%. Okay, and I'm going GA there, just so that I can have the pleasure of adding to your notes that GA means giga annum, and giga means billion, or anything times 10 to the 9th, and annum means year. I think that comes from Latin. That's also where we get the word annual, like every year. So, there we go. If you have not recently reviewed your metric prefixes, now would be an excellent time. Let's think, where are your metric prefixes? Were they in Unit 2? That feels like a Unit 2 thing. Why don't you turn back and see if you can find your metric prefixes? Metric prefixes, let's see. I've got mine on page 70, so great time for a little bit of review. Alright, so that's estimating half-life of radioisotopes, which brings us to to our final page for the day, and at this point, you should have already done the radiation lab. If you haven't, oh my gosh, pause, because I don't want you to overdo this. As you're waiting, you can go ahead and read about radiation you encounter in everyday life. So here we go. These are our different types of radioactive decay. Alpha decay, as we said, 4 particles. 2 of them are protons, 2 of them are neutrons. And this is kind of what it looks like coming off of there. This is an enormous particle. It's just a big, heavy particle as it falls off or gets thrown out of a nucleus. On the other end of the scale, we've got gamma emissions. Those are not particles at all. They're energy. So in this case, it's a little bit more complicated, but essentially what happens here is that the number of particles changes. It's hard to explain. Miss Schrock would do a great job. But regardless, what we get emitted is gamma radiation. So once again, it might be a good time to go back and look at your electromagnetic radiation. In between the two, we've got beta decay, and that's when a negative proton gets thrown off, or like the opposite of a proton. That's called a beta particle. We'll learn more about that after the expert panel, but for now you can just say, it weighs about as much as a proton. So large and slow, low energy, somewhere in the middle, tiny, in fact so small it's not actually a particle, and fast. And in your lab, you should have come to a conclusion about what these particles can get through. Okay, so let's take a look based on your lab. You tell me, how far through different materials can these particles go? This isn't dramatic silence. I'm desperately trying to find it in my own notes. Oh, I'm in this year's notes, which is why I can't find it, because I haven't added it to this year's notes yet. Here we go. So alpha particles are these large, slow particles, and they're actually stopped by a piece of paper. So they're going to get all the way to the piece of paper and then stop. Your skin will also turn them away. Beta rays, or we call them alpha rays as well, beta rays or beta particles are a little bit more high energy. They're sort of high energy electrons. They're the opposite of protons. And they're going to make it all the way through the paper and continue onward, but for the most part, a thin piece of aluminum will stop them. Okay, so like aluminum foil could stop most beta radiation. Now, when we get down to gamma rays and X-rays, these aren't particles. They're not big and chunky and slow. These are literally energy, and they're such high energy, and they're really fast, and actually, they can make it through paper, they can make it through aluminum. In fact, it actually takes a pretty hefty piece of lead to stop these guys, and that's why if you ever get X-rays done at the dentist or in your doctor's office, they'll often put like a really thick lead apron on you. It's really heavy. Now, there are also neutron rays. You can read about those. These are unique, but it's actually so hard to stop these, it takes an enormous amount of water or concrete to stop these. So, these are the different types of radiation. You were kept very safe in your lab because, one, we were only looking at these really low energy ones, and we knew where they were pointing, and you never stood in the direction of the beam, and then we practiced putting different things in their way. So, I'd like you to open this up and read about radiation we encounter in everyday life. It'll actually tell you where you get some of that radiation and how much is too much. And I'd like you to read and annotate as you go, because this is important to understand. The reason it's important to understand is that next we're going to be doing a little thinking about ethics. So, I'd like you to come back. After we talked about nuclear power reactors in the world, we took a look at so many other things that'll help you make decisions about nuclear power reactors. We looked at Yucca Mountain, you've got that reading. We talked about where in the U.S. these things are. We talked about, well, I haven't written it yet, but why don't we do everything with nuclear? We talked about nuclear waste. We talked about, okay, what's the problem with that nuclear waste? We talked about, it's closed, half-life, and then we talked about radiation, what's actually being emitted. So now it's time to ask yourself some questions. You are now a very well-educated individual. There is nothing wrong with being cautious, but once you've been educated, it's time for you to take that caution and decide to what extent is this reasonable. So I'd like you to ask yourself and answer on this page 2 questions. The first question, actually we've got 3 questions, excuse me. The first question is, how would you feel about a nuclear power plant in Gainesville, Florida? Okay, and I want you really to focus on the word feel there. It's not just your intellect and all the things you know. It's okay to think about how you're also feeling about this. Are you feeling safe? One of the important things in our life is felt safety. If you don't feel safe, it's going to be very hard to live a peaceful life. So go ahead and do positive and negative implications in your head. It's okay to be logical about this, just I don't want you to ignore your feelings either. Okay, so some positive implications, for example, high-paying jobs. Some negative implications, well, I don't know that anyone feels incredibly comfortable with the idea of that much energy close to them. So do some thinking on that, and then I want you to write down how you feel. And then skip some lines, because our next question is going to be, actually, how do I want to do this? You know what, we're just doing 2 questions. Just 2 this time. I had another thought, but that's actually kind of a longer conversation. So here we go. Our second question is going to be, okay, however you feel about nuclear power plants, that power is incredibly valuable. We can do a lot with it. It could do a lot for our society. It could do a lot for us avoiding other more harmful types of power. So maybe you don't want a power plant, maybe you do. Let's ask a different question. How would you feel about nuclear waste storage? In Gainesville, Florida. So I want you to do some thinking about each of these, write down some answers, and then I do want you to come and read some of these closely. You might even read these inside articles closely before you write your answer. All right, you'll get a better answer if you've considered all the facts. So go ahead and write these, and if you don't finish these during class today, these are due before you come to class on our next learning day. So the reading day doesn't count, but on our next learning day, we're going to jump into the ethics, and it'll be good to have some of this pre-thinking done. So nicely done, ladies and gentlemen. Thanks for bearing with me. I know it was a lot today. I hope you enjoyed the lab, and yeah, start thinking deeply, because chemistry without application is really useless, and application without considering implications is unethical. So we definitely need to start thinking about the implication side of things if we've decided on the applications. There you go. Do some thinking, then do some writing, and I'd like you to do some reading before you do any of the thinking or writing if you haven't already.